In this video, we're going to look at loci in the Argand diagram. Now, the loci of something, or the locus, is a path which it traces out. So we're going to look at a few different results here and see how we can apply them. Okay, the first one is for two complex numbers, z1 and z2. Then the modulus of z2 minus z1 represents the distance between the points z1 and z2 on the Argand diagram. So if you've got your line z, or your point z1 here and your point z2, then the vector, or the line segment, I suppose, which goes between z1 and z2, so this bit here, is the modulus of z2 minus z1. Okay, the next one, which is very useful, is if you're given z1, which is equal to xi plus I y1, and x1 plus I y1, the locus of point z on the Argand diagram such that z minus z1 is equal to r1, or you could write this as z minus x1 plus I y1 equals r, is a circle, center x1, y1, and radius r. Right, so just to give you a numerical example here of this one, for example, if you had z minus, and we'll just do 2 plus 3i, modulus of that is equal to 5, would be a circle. There's your 2, 3, very roughly here, there's 2, 3. And really give it a radius 5. So that's basically what it's going to be. So if you had something like that, whatever you're taking away, that would be the coordinates of the center. So 2, 3, and the equals, that is a radius. So this one would have a radius of 5, and that's it. Okay, it says in this one, given that z1 is equal to x1 plus I y1 and z2 is equal to x2 plus I y2, the locus of point z on the Argand diagram such that z minus z1 is equal to modulus of z minus z2 is the perpendicular bisector of the line joining z1 and z2. Okay, I'm going to explain this when using two fairly simple points. So if I have, you imagine here, if I have my x-axis, I have my y-axis somewhere over here, doesn't matter, and I have 2 points here, maybe the point, so this would be 4, 0 and 6, 0. Now, if I want to say, if I want to say that modulus of z minus the 4 is equal to the modulus of z minus the 6. So that means that the distance from my point 4 is equal to the distance of from my point 6. So if you think about one point which is between these two, which has the same distance from 4 as it is from 6, the answer would be the point 5. So 5 would be smack bang in the middle. It would be the same distance from 4 as it is from 6. So if you then just take a step vertically upwards, this point is also clearly going to be the same distance from 4 as it is from 6. Take another step vertically upwards, this point is going to be the same distance from 4 as it is from 6, and you can continue that indefinitely. Likewise, if you went down the way, it would be the same. Take a step down, they're all going to be the same distance. So what if I get rid of all those wee bits, what you've actually done is you've created the perpendicular bisector. So this line here is a perpendicular bisector between my 2 points that I have done. So here, if we go back to their example, there's your z2, there's your z1, and then this would represent the modulus of z minus z1 is equal to modulus of z minus z2, because it's a perpendicular bisector of z1 and z2. Okay, on to a few examples on this. So it says, given that z satisfies the modulus of z minus 4 is equal to 5, sketch the locus of z on the Argand diagram. Okay, first of all, this is our circle. This one is going to be our locus of a circle. So z minus 4 is equal to 5 is a circle which has center 4, 0 and radius equal to 5. Okay, so it's a very simple sketch. Remember on your Argand diagram, Your horizontal axis is not the x-axis, it's your it's your real axis, and the vertical axis is not your y-axis, it's your imaginary axis. So you've got the point 4 here, that's the center of the circle. So if I go out a radius 5, that's going to take me to -1, so it's going to take me just left of that, and it's going to take me over this way. Ooh, not bad, not too bad at all. And I'll just do that on down. Oh, won't let me flip that. I'll just do it by hand. Not just so good, but will do the job. So there you have it. Circle, radius 5, and center 4, 0. Okay, next one says find a value of z that satisfies both z minus 4 is equal to 5 and imaginary of z is equal to 0. Right. For this one, for the imaginary of z, I'll do this over here. Sorry, this is B part 1. B part 1, imaginary of z equals 0 represents the real axis. Okay, so first of all, we've got the points, where that means the points where the circle cuts the real axis. Okay, so what would those points be? So remember, we had 4, 0, and we moved on. We had 4, 0, and we moved on 5. That's going to take you to 9, 0. So that's going to be one of them, and the other one, which is going to be 4, and then take away the 5 is going to give you -1. So the points are going to be, so we'll just say i.e. -1, 0, and 9, 0, and that's it. Okay, just read the question again, just check we've got this right. It says find the values of z that satisfy, so it's the values of z, sorry, so this is my point, so give this as a z value. So my real bit is -1, so z equals -1 plus 0i, you would just write that. So values of z are z equals -1 and z is equal to 9. Okay, part 2 says it needs to satisfy both modulus of z minus 4 is equal to 5 and also the real part is equal to 0. So it says exactly the same thing here, except it's a y-axis, where the y-axis or the imaginary axis it's crossing. So we'll just say modulus of z minus 4 equals 5 and real part of z equals 0. So real part of z equals 0 is the imaginary axis. And we'll just say, so to get that, we're just going to say put x equal to 0. So what we have got is an equation of a circle. So we'll just make a, so remember, the equation of the circle is x, this is x minus 4 all squared plus y squared is equal to 5 squared. That's the equation of this circle, because remember, that's an equation, a circle which has a center 4 and 0 and radius 5. So we're going to put x equals 0 into this and see what we get. Okay, so put x equals 0 into that. So i.e. that's going to give you minus 4 squared plus y squared is equal to 25. So 16 plus y squared is equal to 25. Y squared is going to be equal to 25 minus 16, which is going to be 9. So y is equal to plus or minus 3. So we'll just say the points, the circle crosses the imaginary axis are, so 0, minus 3, and 0, positive 3. Now read the question. I think I made this mistake in the last one. Yep. It said to give you the z value, so that's not the coordinate. So the z values of these, remember, this means 0 real, but minus 3i, 0 real, and positive 3i. So answer for this one, z is equal to minus 3i, and z is equal to positive 3i. Okay, this example says complex number z is represented by the point P in the Argand diagram. Given that modulus of z minus 5 minus 3i is equal to 3, sketch the locus of point P. Okay, first thing I'm going to do is I'm going to change this so it is in the form z minus something. So I'm going to write that as z modulus of z minus brackets 5 plus 3i equals 3. Then it's dead easy for me to see that this thing is a circle. See, believe it or not, a circle, center 5, 3, and radius is equal to 3. So if we just sketch this thing, there's my circle, there's 5, and then 3 is going to be here. So that's, I'll just mark on that point as 5, 3. And if it has a radius 3, it's going to go down, it's going to touch the axis. It's not going to touch the, so it's touching the real axis, I should say. It's not going to touch the imaginary axis. That's only going to be 3 is my radius. So that's 3 down to here as well. Okay, now use your imagination as if that's a circle, please. Okay, part B says find a Cartesian equation of this locus. So I would just go back to what you've done last year in your A-level mathematics. So your center is 5, 3. So it's going to be x minus 5 squared plus y minus 3 squared is equal to r squared. We'll write that as 3 squared in this case. And then, you know what, I would just leave it as that. That is absolutely fine. So we'll just say that's x minus 5. Well, I'll just multiply the 3 squared, x minus 5 squared plus y minus 3 squared is equal to 9. And that's it. Okay, next part C, you can see I've changed my circle here, made it a wee bit better so we can see this a wee bit nicer. It says find the maximum value of arg z in the interval minus pi to pi. Right, so here what we want to do is we want to find the greatest gradient basically from here, if I was to draw a line to anywhere on this circle. So you can see if I, first of all, this is just the gradient is going to be 0. Here, the gradient to this point is going to be better than 0 definitely, but the maximum is going to be here where it's a tangent to the circle. So to do this, first thing we've got to do is draw a tangent to this circle. So I'm going to do this as best as I can. So that's where it's going to go. And then you should use your knowledge of circles to know that a tangent meets at right angles. So we need to find this whole angle all the way from here to here. That's really what we're wanting to do. So not easy to do. So we're going to have to piece together and figure out a few things. So remember that was 5, 3 was the center. I've now created a right angle triangle. And if I drop another perpendicular down, I've got another right angle triangle. So I know, let's mark on this thing all the lengths that I know. I know this is 5, this is 3. That means I could find this angle. And if I find this angle, that has found, I can double it to get this whole angle. So what we have here, that's theta over 2. I'm looking for the whole theta, and that's theta over 2 as well. So we can use a wee bit of trig to find my theta over 2, and then we'll just double it to give you your angle theta. So we'll label this is O. We'll call this point C for the center. We'll call this point A over here, and we'll call this point here is going to be point B. So we'll say in triangle OBC, we will say that tan of, and that's going to be theta over 2. Tan is equal to opposite over hypotenuse, so it's equal to 3 over 5. That means theta over 2 is equal to tan to the minus 1 of 3 over 5. And that means, I'll just write it as that, tan to the minus 1 of 3 over 5. There's no need to actually work it out. Just say, therefore, theta is equal to 2 times tan to the minus 1 of 3 over 5. Therefore, your arg z, and it's a maximum, brackets maximum, is equal to 2 times tan to the minus 1 of 3 over 5. And let's just do that on a calculator to see what we get. So calculator into radians mode, and then we'll just do 2 times tan to the minus 1, 3 over 5, press equals, and I have got 1.08 to 2, 1.08 radians to 2 decimal places, and that's it. So, okay, it says here, given that the complex number z equals x plus iy satisfies the equation z minus 12 minus 5i, modulus of that is equal to 3, find the minimum value of mod z and the maximum value of mod z. Okay, first thing I'm going to do is diagram. Before I can do my diagram, I have to just say I'm going to rearrange this thing so it's in the form that I like. So z minus 12 plus 5i, modulus of that is equal to 3. So I now can see this is a circle, center 12, 5, and the radius is equal to 3. Okay, so how we go drawing that, and then we'll look at the question. The next example says, given that modulus of z minus 3 is equal to modulus of z plus I, sketch the locus of z and find the Cartesian equation of this locus. Okay, the first thing I'm going to do in solution is I'm going to write this in the form that I like. So modulus of z, minus 3 is equal to modulus of z minus I. So I can see what the form that this thing is going to be in. So this means this is a perpendicular bisector of the point 3 and the point minus I. So this is what we're going to have to be drawing here. Okay, so to do this, we'll just label those 2 points. So we want to say, sorry, it's perpendicular bisector of 3, 0 and 0 minus 1. So first thing we're going to do is find the gradient of 3 between 3, 0 and 0 minus 1. So we'll do that first of all. So gradient of line joining 3, 0 and 0 minus 1 is going to be equal to, so your y difference is going to be 0 minus 1 over 3 minus 0, which is just going to be 1/3. Therefore, perpendicular gradient is going to be minus 3. So your line so far, remember y equals mx plus c, is y is equal to 3x minus 3x plus c. It's a perpendicular bisector, so what we've now got to do is bisect the points 3, 0 and 0 minus 1. So we'll just say that is a mid to give you your midpoint. So midpoint of 3, 0 and 0 minus 1 is equal to 3 plus, sorry, that's, that's right, 3 plus 0 over 2. And then my y bit is going to be 0 plus minus 1 over 2, which is going to give you 1.5 and minus 0.5. So you've got your midpoint. You can then put this midpoint back into your y equals minus 3x plus c and see what you get. So just say sub into y is equal to minus 3x plus c, and that will give you minus 0.5 is equal to minus 3 times 1.5 plus c. So that's been minus 0.5 is equal to minus 4.5 plus c. And 4.5 comes with minus 4.5 comes across and becomes plus 4.5. So 4.5 minus 0.5 will just give you 4 is equal to your c. And your last line is just rewrite your equation. So your equation is therefore it's y is equal to minus 3x plus 4. Okay, you're good to go. You've now done that. You can just do your sketch. We can sketch it really well now. If you hadn't done that, folks, by the way, and it just asked you to sketch the thing, you could have just done it, and because you knew it was a perpendicular bisector, and the points were 3, 0, and then it was minus 1. So minus 1 and 3. So that's where it was bisecting. So you could have just done a very rough sketch. So do a line joining on 2 of those, and then just show how it is by a perpendicular bisector. That would have been fine. But because you've now got your line drawn, you've now got your Cartesian equation, you could draw the thing a little bit more accurately as well. And that's it. So you've got your line. This is your perpendicular bisector, and that's it done. Okay, I'm going to show you another way we could have done that question. So this is still part A, but this is another way of doing part A. So I'll do this in black. So part A, I'll just say or. So this is another way of doing it. So you may look at this and you might think this is a much easier way of doing it. There are times when you will need to do the way I've just shown you to start with, so it's not been a waste of time. So whatever one you prefer, but I'd imagine you'll prefer this method. Now for this method, all we're going to do is rewrite your z in terms of x plus iy. So that's modulus of x plus iy minus 3 is equal to modulus of x plus iy minus I. And that's going to be x minus 3. I'm just separating the real parts and the imaginary parts. That's all I'm doing here. That's going to be x plus, and that's going to be I times y. Oh, sorry, that was plus I over here. I'll change that as plus I. So that's going to be y plus 1. And then we're going to do the modulus. Now the modulus, remember, of something is the real bit square root of the real bit squared plus the imaginary bit squared, and again square root of the real bit squared plus the imaginary bit squared. So we just do that out. You're going to have the square root of x minus 3 all squared plus y squared is equal to the square root of x squared plus y plus 1 all squared. And if you go on from that and see what happens. Well, first of all, I would square both sides, get rid of the square root signs, and then just square out those things. You're going to get x squared minus 6x plus 9 plus y squared. That's our left hand side squared out. The right hand side squared out is going to be x squared plus y squared plus 2y plus 1. We'll just bring it all, leave all the y's to one side, and I'll bring my x's all to the left hand side, including my x squareds. Now the x squared terms will cancel out, and you'll have minus 6x plus 9 minus 1 is equal to 2y, because our y squareds will cancel out when they all go to the other side. So I'm just going to write that as 2y is equal to minus 6x plus 8, which means y is equal to minus 4x plus, oh, if I could divide by 2, that would be good. Y is equal to minus 3x plus 4. So there you have it. You have the two ways of doing part A. Okay, we're going to go on now and look at part B. So we'll go back and have a look at what the question said to us here in part B. Part B says, find the least possible value of modulus of z. Now remember what modulus of z is. It's a distance from your origin to something on this line, and that's going to be it. Okay, so we'll have a look at this down here. Okay, so we want our least possible value of modulus of z. So it's going to be this. It's the shortest distance it takes you to get from here, the origin, over to your line. And if you should know by now, the shortest distance to get anywhere is when you meet it at right angles. So that's our origin O, and that is P. So we've drawn that in. So we'll say least distance will be OP, and we need to find out what that is. Okay, what do we know about O and P? We know it makes it perpendicular. So we'll say the gradient of your line OP is equal to positive 1/3. Okay, and that means therefore equation of OP, because it goes through, the equation of OP, because it goes through the origin, the equation is going to be, because it goes through the origin, the equation is going to be y is equal to 1/3 x. There's no intercept, as the intercept really is 0. So we want to find out where this line meets your perpendicular bisector. So we need to find out, I'm going to raise that thing, find out where OP meets your perpendicular bisector. And the equation of that perpendicular sector was y is equal to minus 3x plus 4. So it's a nice easy bit of mathematics now. So you've just put the two things equal. So 1/3 is equal to minus 3x plus 4, which means 3 1/3 x is equal to 4. And then x is equal to 4 divided by 3 1/3. I would just do that on my calculator, and that gives me 6/5. Okay, so just say, after you've got that 6/5, just put that into your anything at all. I'm going to say put it into, so when x equals 6/5, my y is equal to 1/3 times 6/5, and that works out to be 2/5. We've got our point, we've got our point P, so we now know that P is equal to 6/5, 2/5. So therefore your distance OP is going to be equal to the square root of 6/5 squared plus 2/5 squared. And if you do that out on your calculator, I'm just going to skip a wee bit of working out. That's going to be 2√10 all over 5, and we'll just give it a, say, units, and that's it. Okay, if you have a point z1 is equal to x1 plus I y1, then the locus of point z on the Argand diagram such that argument of z minus z1 is equal to theta is a half line from the z1. So here it makes the angle, you've got the wee horizontal dashed line, and it goes up through here. That's your argument, theta, and it's this half line. It does not go on through, so that's very important. It just cuts off there. So I'm just going to do a wee example of this. So example, if you had argument of z minus, and I'll put it in the form I like, 1, 2, so 1 plus 2i, I should say. So if it's in that form, dead easy to see, is equal to pi over 4. So to do this, you just mark on your point, which is 1, 2, and then it's just that 45-degree line, or pi over 4, I should say, in radians, and that's it. So that's all you're looking for in this case. If we change this, for example, and this was maybe 3 pi over 4, then 3 pi over 4 would mean that this would change. This angle now would become 3 pi over 4, so it's going to be out this way. So that's going to be 3 pi over 4, and that's the way it's going to be out here. All right, so it's a half line going from the positive direction, and that's it. Okay, we're going to look at the example on this and see how we can work with it. This example says, given the argument of z plus 3 plus 2i is equal to 3 pi over 4, sketch the locus of z on the Argand diagram. Right, first thing I'm going to do is I'm going to rewrite my equation in the form I like. So it's always z minus something. That's why I make it z minus something. So it's going to become minus, in the bracket, minus 3 minus 2i is equal to 3 pi over 4. And then we can just do a wee sketch of that thing. I'll zoom down here so I can see it. So I've got my imaginary axes. I've got my real axes. And then this was my point, minus 3, minus 2. Your dashed line for your horizontal. And 3 pi over 4 would be this sort of angle. So use your imagination again, that's a straight line. And that's it done. Okay, so that's part A done for us. Part B says find equation of the locus. So that means we want to find the equation of this straight line. So remember, we know what this is. We know that this line goes through the point minus 3, minus 2, and we could work out very easily the gradient. So you can just sub that into your y equals mx plus c, or there's other ways of doing it as well. Okay, first of all, we're going to look at the gradient of this line. Now, if you have any line here, for example, there's a straight line, its gradient can be given by the this angle here. This is the angle, but the gradient is given by tan theta. Now let's think about why that is. Tan theta is equal to your opposite over your adjacent, and opposite over adjacent is the same as your y difference over your x difference. So basically, if you have the angle theta, tan theta gives you the gradient. So that's what we're going to be using for this. Now that was written down in your notes earlier on if you want to go back over that. But that's it. So if you want to find the gradient of a line and you've got its angle, and its angle is, say it's pi over 4, then your gradient is going to be tan of pi over 4. Okay, I'm going to get rid of that, and we'll look at this question for part B. We're going to show you two methods for doing this. So first of all, your method 1 then for this is for part B. We'll say your line has gradient tan theta, i.e. tan of, in this case, 3 pi over 4, and if you do that, is equal to minus 1. So it also passes through the point minus 3, minus 2. So far we know y is equal to minus x plus c, and then we're going to sub in minus 3, minus 2. So that's going to be minus 2 is equal to minus 1 times minus 3 plus c. So minus 2 is equal to 3 plus c. So that's minus 5 is equal to c. Therefore, y is equal to minus x minus 5. Okay. The other restriction on this, folks, is we have to say that your x has to be less than minus 3. So this line, it doesn't continue all the way through. That's the equation of this line is definitely y is equal to minus x minus 5, but it doesn't exist over here. So we'll also have to put a wee restriction on it to say and x is less than minus 3, and that's it done. Okay, we're going to look at another way of doing this same question. So we're going to I'll do this in black this time. So it's the same question, same part B. We're going to look at just a second method. Okay, the other way of looking at it, we have arg of z, it was plus 3 plus 2i is equal to 3 pi over 4. Now we're going to use the fact that we know that z is the same as x plus iy, so we're going to write that as the x plus 3, so I've grouped the real parts, and then plus I times my y, my imaginary parts, which are y plus 2, is equal to 3 pi over 4. So what that means, the argument of this thing then, this really means you've got y plus 2 over x plus 3. That's my gradient, because this means I go 3 over 2 up, and I go x plus 3 across. Sorry, y plus 2 up, and I go x plus 3 across. That's my rise. So that's my rise over my run. So that's going to be my gradient, and it's equal to, the gradient, remember, is tan of 3 pi over 4. So we'll just work with that. That means y plus 2 over x plus 3 is equal to minus 1. Then multiply across, you're going to have minus x minus 3, and then that's going to just become y is equal to minus x minus 5. Now I have to admit, I do not like this method just as well as the first one. I prefer the first method, whereas for the previous example, I think it was, I definitely preferred writing it, doing this form, for I think it was a perpendicular bisector. So you may be different, you may prefer this one and the other one in the first, or you may prefer both of one, it doesn't really matter. Okay, your last thing to say then here is as well, remember, just flipping back to our line only exists whenever x is less than minus 3, so just say and x is less than minus 3. Okay, part C of this question says find a complex number z that satisfies both modulus of z plus 3 plus 2i is equal to 10 now, and argument of z plus 3 plus 2i is equal to 3 pi over 4. We'll have a look at how we do this now. Okay, part C. We've got modulus of z plus 3 plus 2i is equal to 10. And again, I'm just going to rewrite that as z minus 3 minus 2i is equal to 10. And that is a circle, center minus 3 minus 2, and my radius is equal to 10. So I'm just going to draw that out for us now and see what we've got. Okay, so you've got your imaginary, you've got your real, and there is your bit of a circle. There's your origin. I'm not drawing the whole thing, I'm just drawing the bits that are key to us. And we had, this was our minus 3 minus 2. And this was our original line. The radius of this thing was 10, so that's very important. We're going to drop a wee perpendicular down to this, so it's going to be fairly basic trig we're going to be using to do this. And that was pi over 4. Remember, that angle was, as this whole angle was 3 pi over 4. I could have drawn this onto my original diagram, but I just didn't want to confuse the earlier part. Okay, now I'm going to call this wee height A. I need to find out what this wee height is. And this wee height is also going to be A because pi over 4, remember, is 45 degrees. So that's going to be a nice sausage triangle. So if this wee height's A, this wee horizontal is also going to be A as well. So we can find A by Pythagoras. So we'll just say that by Pythagoras, A squared plus A squared is equal to 10 squared. That means 2a squared is equal to 100, which means a squared is equal to 50, which means a is going to be equal to, and it's going to be equal to 5 root 2 as an exact value. So that means we wanted to find, the question asks us, I forgot what the question says, the question asks us to find the z, the complex number z that satisfies both of these things. So to satisfy both those, it has to be at this point. So it's on your line and it's on your circle. So that means your z is going to be equal to. So we've started at your minus 3, and then you've gone back left. You've gone left 5 root 2, and you've started at your minus 2, and you've gone up 5 root 2. So your z is going to be equal to minus 3 minus another 5 root 2. Plus I, and you're at minus 2, but this time you're going up 5 root 2, and that's it. So z in this case is going to be equal to, that's all it is. Actually, we've got it. We don't have to tidy it up, and that's absolutely fine. We'll leave it as it is. Okay. Right, folks. One other way you could do this, I'm just going to write out the instructions for this one, and you can work through this one in your own time. Or what you could do is sub the equation y is equal to minus x minus 5. That was your half line, remember, into the equation of the circle, which would be x plus 3 squared plus y plus 2 squared is equal to 10 squared. And solve and then solve to get the z values. Then, very important, then choose the appropriate one. Right, now what I mean by that, choose the appropriate one. You will, if you put this line into this equation and then solve, you're going to get the answer over here, the x and its corresponding y value over here, and you're going to get the one that would have been down here on the circle. But remember, it's only a half line, so it's only going to meet this circle one time. So you'll have to know from your diagram which one it's going to be. So it's going to be the one that's left and up of your center, as opposed to the one that's down and right of your center of your circle, minus 3, minus 2. Okay, folks, that is us done for this video. A very long video, apologies. Excel book, questions, exercise 2E, questions 1A, C, E, and I, and then 4, 6, A, C, E, and I, and then 7 and 10, A, C, and E.